the manager for the West Coast, and I will be giving the webinar on improving the performance of MEMS designs using dynamic characterization. So over the next 30 minutes, I'd like to show you how our instruments are used for vibration dynamic testing of MEMS structures. So a little bit background on our company. We make an instrument called the laser Doppler vibrometer for fast, accurate visualization and analysis of structural vibration. This instrument is used in quite a number of fields. For large structures, for measuring the full body of cars and airplanes, where it would be difficult to use contact sensors, we can use a laser and scan over the full surface. For structures that are difficult to reach, like wind turbines for health monitoring, it's an advantage to use a laser to measure those. And for measuring small structures, like MEMS and data storage, where the only technique that you can use would be non-contact for measuring really small devices. So for this webinar, what we're talking about is Micro-Electro-Mechanical Structures, or MEMS. So doing the dynamic characterization of these. So first of all, what's a laser Doppler vibrometer and how does it work? Laser Doppler vibrometry, or LDV, is a laser interferometry technique. The idea is that you have a laser source. That laser source, you can split the light. One laser beam targeted at the vibrating object. The other laser beam is a reference beam. The light that's targeted and backscattered from the object has a Doppler shift, a frequency shift directly related to the vibration of the object, the velocity. This frequency shifted light is interfered with the original beam, and then you have an interference pattern. That interference pattern we measure with a photodetector, and then we demodulate it and decode it to a real-time velocity or displacement output that you can measure as an analog output. So we have both capabilities for velocity and displacement, and the important thing is that we can measure these real-time using the laser Doppler vibrometry technique. So our system that we have for MEMS characterization is our microscope-based system. This is our microsystem analyzer, or MSA 500. It uses this technique for laser vibrometry and combines other techniques for precise 3D analysis of structural vibration and also static surface topography. So we combine these powerful tools into one instrument for dynamic and static characterization of MEMS. And we use a scanning technique to scan and then map out out-of-plane deflections, and I'll describe how that works. So our MSA 500 has both laser Doppler vibrometry, which I'll be talking about, scanning vibrometry, stroboscopic measurements for in-plane measurements, and also white light interferometry for static shape measurement, all combined into one tool. And then this shows you basically the stroboscopic. So for in-plane motion, we can measure in-plane motion using strobe techniques. So the vibrometer measures out of plane. In-plane we can measure with combined strobe video microscopy. And then also the white light interferometry for doing shape measurements. So we can do static shape measurements to determine step heights, roughness, depth, shapes, those sorts of things also. So how does the scanning technique work? So the scanning technique takes the laser beam from the laser vibrometer and then scans the surface to map out the deflection shape over the whole surface. So in the example that I'm showing here with a piezo motor, we have a piezo motor device. We want to map out what the deflection shape looks like that. So we first start with a microscope video and we zoom in on the area that we want to measure. And then we grid the measurement with measurement points. So we can assign however many points we want to the object. We can grid it, say, with hundreds, thousands of points, place the points wherever we want to on the structure. And then those are the points that we'll actually make the measurements with. And then we excite the structure, so we run it or activate it with a drive waveform. We go to each point and we measure the vibration time signal, the actual response. This is a real-time response at each point. What we do is we capture that response for a single point. We can capture that as a time response or an SFT response, depending on the analysis that we want to do. So if we want to look at actuation, we can look in time. If we want to look at resonant frequency and modes, then we can look in that in the frequency space using an SFT. and then look at the resonant frequencies down the spectrum. Once we captured that for a single point, then we go to the next point and measure it. So we do a sequential measurement. So we measure point by point on the structure until we've measured every single point on the grid. Once we've captured all that data, our software takes that data and then builds up a deflection shape. So what you're seeing on the screen there is an animation showing you both the phase and magnitude for that structure at a specific frequency, in this case 36 kilohertz. And you can see there's a nice processing mode there for the piezo motor. Intuitively, this shows you how it works. You can see how that mode actually travels around the structure, and then you're able to visualize what that vibration is using the scanning technique. One important point for the laser vibrometer is it has to be a sequential measurement. We can't be at every point simultaneously. We have to scan point by point on the structure. So we require a repeated excitation. You have to repeat or continuously run the excitation. We don't have to synchronize it necessarily, but we do need to repeat over and over again the excitation as we scan point by point. So what we do is we couple this into a microscope. So in order to measure on microstructures, the important thing is that we can couple this into a microscope and achieve the optical resolution required to look at things that are on the micron scale. So what we're doing is coupling the laser measurement light through the microscope and then focusing it down with a microscope objective. We're able to achieve spot sizes down to microns level using this. And our resolution is down to submicron. We can't do better currently because diffraction limits for the visible light, but we're able to achieve down to say 0.7 microns. And then we use scanning mirrors to scan the laser beam over the surface point by point and collect the response data and then actually map out the vibration. This is also coupled with an LED illumination that's used both stroboscopically to capture the in-plane, and then also for the white light interferometer, that's the light source. And then the camera's coupled in, so you have a complete optical system. We can interchange the lenses for long-range lenses, so you have a full range of long working distance objectives, all the way from 1x all the way up to 100 or even 200x. So what are the advantages of laser vibrometry? One really distinct advantage is we're able to measure real-time response. So it's a signal-based measurement. We're able to use it, measure the response as it happens, which is a huge advantage because we don't require post-processing. So you know right away if your device is moving because you can see the response on the screen like you would an oscilloscope, and then see the movement. And then we can also measure down to picometer resolution. A picometer is 10 to the minus 12 meters. It's 1/1000th of a nanometer. It's very high displacement resolution, so we can measure both real-time and the smallest of vibrations, which is very unique capability. We have high spatial resolution, as I talked about, down to 0.7 microns. We can measure from DC up to gigahertz frequencies. Our standard version goes to 24 megahertz, but I'll talk about an ultra-high frequency system that's now capable of 2.5 gigahertz. Our accuracy is very high because we're using a laser interferometer. Our ruler, if you will, is the wavelength of light. So that creates a high accuracy. We have less than 1% measurement error. And we could do difficult measurements under different environmental conditions, temperature, humidity. Also, we could do measurements in vacuum. So one thing that I'll show is ability to measure in vacuum chambers. And we can integrate with a probe station, so we can do measurements at the wafer level. An add-on to this is our white light interferometer. This adds an additional capability for topography measurements. And this allows you to do static characterization too. So this talk is focused on dynamic measurements, but just to mention, there is an add-on capability. We can look at microscopic measurements of step height, curvature, flatness, roughness, and form parameters such as dimensions, angle, and radius. So it's a modular system. So we have this add-on capability to do topography measurements. So you can configure and tailor the system to whatever your needs are. Topography and dynamic characterization. 3D characterization, high frequency measurements. So one question that gets brought up is, can we do measurements in vacuum, in a vacuum chamber? And the answer is yes. We've actually configured this system with vacuum chambers. So a lot of devices are designed to work in vacuum because of the damping from air damping. So we're able to basically target our measurement beam, laser beam, through the glass in a vacuum chamber and then measure down into it. So you can see the example here. This is a vacuum chamber from a partner company, MMR. We're able to instrument this and then measure through the glass into the vacuum under vacuum environments and then measure the response. So this is actually a vacuum probe chamber. So you can actually drop probes on this, lower the vacuum, and then you also have the capability for temperature control too. So this is kind of a neat setup because it's pretty flat, compact form factor and works well with our system. So we have information on that too. So what are some of the examples of how this technology is used? So I'm going to show several measurement examples. The first one's of a comb drive actuator. So this is one that we've long had in our examples going back quite a bit, but the idea is that this is an in-plane actuator, but it has complex 3D motion. So it's a good test object. This one in particular is from Sandia National Labs. So it's an in-plane actuator. The idea is that you have a central mass. You're exciting it with electrostatic voltage on the combs, which creates a pulling force that moves the central mass. There's a restoring force from two springs. And then you have a characteristic resonant frequency for the device based on the mechanical properties. So the dimensions, thickness, modulus elasticity, spring constants determine what the resonant frequency are. So we're able to measure that with our instrument. In this particular case, this was fixtured on a chip. We were able to make the electrical connections, put this on a vibration damp table, and then basically micro-position the device into place and then run this from our frequency generator to excite it and then do the measurement. So the actual measurement, we took the structure. The structure's several hundred microns in size. We were able to grid the comb drive shuttle with 700 points over the surface. We were able to excite this with a frequency sweep. So with using an amplifier and then sweeping the frequency from 0 to 2 megahertz, we were able to excite the full frequency range for this device and drive it for those frequencies. Each point, the frequency sweep or the chirp was 12.8 milliseconds. So in 12.8 milliseconds, we came up with the full frequency response for the device. And then there's the frequency response. So you can see already we've identified 11 resonant frequencies. The fundamental frequency for this is 13.8 kilohertz, but you can see you have resonant frequencies all the way down the spectrum. So very quickly, we can look at what the resonant frequencies are for this device and then map that out for each point. So it automatically goes and scans and captures this response point by point. Then the end result is a deflection shape. So this is showing you, oops, let me go back one. This is showing you the deflection shape for this device at the fundamental frequency of 13.8 kilohertz. So you can see that's 30,000 points measured on the structure, and you can see we can map out in detail what that deflection shape looks like. So that's actually 13.8 is an in-plane mode. What we'd like to see is actually the full 3D response. So combining that with the strobe measurement, we're able to look at the full 3D response. So this measurement combines both the out-of-plane and the in-plane using the strobe, and you can see, okay, as it's actuating at the 13.8 kilohertz, it's going back and forth, but there's also a electrostatic force between the ground plane and the object that's lifting it up. So there we've got a full 3D characterization of the motion at the fundamental frequency. You can see there's combined in-plane and out-of-plane response for the device. So we're able to do full 3D characterization of this device. Another capability that we have for characterizing MEMS is looking at ultra high frequencies. So we're able to look at resonators and devices that go out to gigahertz frequencies. This is using our ultra high frequency vibrometer, or our UHF 120. This is a specialized system that we have for looking at these frequencies. So the current capability is 2.5 gigahertz on the system. It's a specialized system, and so far that's what we're able to push the frequency out to. So the application for this would be looking at resonators, both bulk acoustic resonators, SAW devices, and things that vibrate at those frequencies. So the way it works is basically it's a laser interferometer using the same technique, but we have a high frequency front end that's able to capture the response, the interference signals out to gigahertz frequencies. This is combined with a function generator driving at those frequencies, and then our software to capture and run the measurements. We do a stage-driven measurement, so we're able to drive the laser spot from point to point using a stage. We collect all the response, and then we're able to map out both the phase and magnitude over the structure. Some of the specifications for this, so compared to our MSA 500 that I just showed you, this system, I need to update it. It's beyond 600 megahertz. It can go out to now 2.5 gigahertz. We're able to measure high velocities, and the resolution is also sub-picometer, so we can measure down to very, very tiny vibrations using this. It actually uses a green laser for this, class 3 laser. So the example that I want to show for this is measuring on a SAW device, or a surface acoustic wave device. The idea is that this SAW filter, basically you generate a acoustic wave using an input transducer. This is exciting at 262 megahertz. It has interdigitated fingers that creates this wave. This travels across a substrate, so you have a substrate material. The wave typically attenuates as it goes across, and then it's picked up by an output transducer. And this is used as a filter, so you can actually filter the frequencies, and this is what's used in cell phones currently, SAW devices, and then F-bar resonators for filtering out signals. So the measurement that we did on this shows you the traveling wave there at 262 megahertz. So we're able to map that out in quite detail and then show you what that looks like. So that's both the phase and magnitude. This wave is actually down on the 4 picometer scale, but you see no problem measuring it. And the wavelengths for this are in the micron. So we can actually accurately map out what that wave looks like traveling across the substrate, both phase and magnitude, and see how that couples across the device, what the attenuation is, and what the wave structure looks like. A last example that I'm going to show are example measurements we've done with using a new infrared vibrometer technique. So one of the questions that we get asked is, Polytec, can you guys measure through cap devices? So if you have a device that's encapsulated, it's underneath a silicon cap, typically those wouldn't be possible to measure because those would be covered up by the cap. But infrared is basically silicon's transparent to infrared. So there's infrared imaging techniques where you can look at encapsulated devices. Here the goal is to develop an infrared vibrometer where we can basically shoot the laser through the silicon cap and do the same measurement inside encapsulated devices. So this project is called IRIS, Infrared Metrology for Inline Inspection of Capped MEMS Devices. The idea is to do the same vibrometry measurements for encapsulated devices. So here's the concept, is basically to use our laser vibrometer, shoot it through the top cap. You can see a cap surface there with a cutaway showing the device, and actually target the laser on the device underneath to do the same dynamic characterization. So to look, okay, are there any flaws or things that occur to the device because of the encapsulation process or the fabrication process? If there is, try and characterize it and find out what's happening to your device once it's encapsulated. So this is just basically a prototype, but we have an infrared vibrometer. We're able to couple it down with microscope lenses and then take a look at devices. So this was an actual example that we did with Bosch for measuring their device. So we were able to target the laser beam through and then look at the resonant frequencies and pick out, okay, there's out-of-plane resonances higher than 1.5 kilohertz, and then determine the amplitude of those responses also down on the picometer range. This is kind of a neat capability. We're still in the process of developing it, but it's something that we'll have pretty soon for looking at encapsulated devices. So this was a short presentation just showing the capabilities that we have for MEMS characterization. So to recap, we have a range of tools for MEMS characterization. The real important takeaways is that we're able to measure real-time response. We don't have to post-process our results, but we can look at them live as they're happening. We have a very highly sensitive measurement with the resolution down to picometer level. We're able to measure broadband frequency response with microsecond or even now sub-microsecond times, and it's an all-in-one solution. So we're able to combine laser vibrometry with other techniques like white light interferometry and stroboscopic measurements to do full 3D characterization and topography measurements. And our instruments are extremely well supported by our application engineers. I've been with Polytec for 22 years. I'm very familiar with MEMS applications and support those throughout North America. So that concludes our presentation. I hope you've enjoyed it. So now we'll open it up to any questions you guys might have.
Perfect. Thank you, Eric, for this very interesting presentation, introducing us into the world of dynamic characterization of MEMS. And Eric will now start the Q&A session. Any questions that cannot be addressed during this session, again, will be followed up by our technical staff within the next 2 days. Okay, let's start then with the first question. Eric, what is the typical test time for a measurement, and how can I estimate?
Yeah, the typical test time for a measurement depends really on what type of measurement you're doing. So if you want to measure 1 point, as I showed in the example, we can test the response in less than a second for a single point. If you want to scan and map out the deflection shapes, depending on how many points, this could be tens of seconds to minutes to hours, depending on what you want to measure. So typical measurement, say of 100 points, could take several minutes. If you want to measure 30,000 points, looking at wave propagation going across the screen with micron resolution, some of those measurements for doing wave propagation could take up to an hour or so to have that level of detail. So we measure point by point. So really the measurement depends on how many points, what frequency, and what sampling time you have.
Okay, thank you. Second question here, does laser spot cause a temperature change that can interfere with the measurement?
That's a good question. So we're using a 1 milliwatt Heine laser to do the measurement. So typically that doesn't cause too much, that doesn't really heat up the sample. It's not enough energy in most cases to heat up the sample. What could happen is under vacuum, for a very small device, like say like a micromirror or something like that was really small, like 10 microns, very thin and in a vacuum, that could heat up the structure. So in that case, you want to be careful of that. And what you could do is either dim the measurement beam, or you can gate the measurement beam on and off. So you can turn it on for a second to do the measurement and then turn it off while the measurement's not running. So that's something you could do in the case where you have something that's thermally sensitive. In most cases, the stuff I showed with the MEMS comb drive, there was no thermal sensitivity to the laser beam.
Okay, thank you, Eric. I have last question, unless something comes through in the meantime. But last question here is, how can we eliminate background vibration when measuring at low frequencies, like picometer levels?
Yeah, that's a good question also. So Background vibration, it's important to eliminate that, especially if you're measuring in that range. So, of course, we're able to measure down to picometer, but background vibrations can be at that level or even higher, nanometer level, especially for ambient vibration, say less than 100 hertz. So people walking around in your building, all sorts of things. So we recommend putting this on a vibration isolation table. So you can float it on a table. That will isolate, eliminate most of the background vibration. Also, if you're measuring above those frequencies, you can high pass filter the response. So if you're not interested in anything that's below 100 hertz, you can set a high pass filter at 100 hertz and then basically knock out all of that background vibration. Since we're a signal-based measurement, it's possible to apply filters to it. So I'd say by a combination of vibration isolation and applying filters, you can eliminate most of that.
Perfect. Thank you, Eric. I don't see any more questions for today, so thank you again for your presentation and for elaborating on the questions. And
thank you.
This brings us to the conclusion of the Q&A session and today's technical webinar. And if you have any additional questions you would like us to answer, please feel free to continue and enter them. Thank you very much for attending today's seminar on dynamic characterization of MEMS, and we're looking forward to welcoming you again to any of our upcoming webinars or events. Thank you for your attention and have a great day.